Okay, let's begin, gang. See this anvil? About 60 pounds. 60 pounds. Heavy or light? Begin with the H. No, H, okay? That is heavy, okay? If that anvil all of a sudden started like scooting across the table, you would look for some reason for that, wouldn't you? Maybe you'd look for maybe a rope that you can't see, or maybe a magnet or something. This is just not going to move of itself, is it? There's going to be a reason for it to move. Hey, this is 20th century. We know there are reasons for things, right? If I take this ball, okay, this ball, put this ball, that ball starts all of a sudden going up in the air. You'd look for maybe a string that you can't see or something, right? Things don't move of themselves, do they? Or do they?
Poltergeist?
Yeah, or do they, okay? We're going to talk about that. A fellow by the name of Aristotle, who was a giant for the human intellect in advancing humankind, way back 4th century BC, classified many things and brought knowledge to a very, very high point. But Aristotle made some mistakes. And not to emphasize his mistakes, but one of the mistakes Aristotle made was that if something's moving, again, there's got to be a reason for it. Things don't move of themselves. And so he said if something moves, it's because there's a force pushing or pulling. This thing started moving. You'd look for a force, wouldn't you? Aristotle also. And so he made that one of the dictums, that if something's moving that doesn't ordinarily move, then there's a force acting. And boom, that was carved in stone in the medieval years. But it bothered some people. Because, take, for example, a cannonball shot from a cannon. Here's a cannonball, okay? You put that inside the cannon. What makes the cannonball move? Well, you got some gunpowder back here. You ignite the gunpowder, it expands. Got no room to expand. What's in the way? The cannonball. And so what's the cannonball do? Moves. And the gunpowder pushes the cannonball out. No mystery. Here was the mystery. Once the gunpowder has spent itself and the cannonball is outside, it's still moving. What's keeping it moving now? Woo! You take a bow and an arrow. You pull the arrow back. You let go. Boom! It's easy to see what makes the arrow move. That string is stretched right again. That string is pushing on it. That's what moves. Fine. But when the string is no longer pushing, guess what, gang? It keeps on moving. If it's moving, there's got to be a force. Got to be a force? Where's the force? And so the scholars of those years tried to find where the force was. And they come up with this idea. When that cannonball is going through the air, it's parting the air in front. The air's got to get out of the way. It leaves like a... You guys don't be knowing about snowbanks. But if I take this thing and throw it into a snowbank, you guys know what that is, a snowbank? A bank of snow. You know what would be left behind? A hole in the snow, okay? And it was reasoned that as this moves through the air, it leaves behind a hole in the air. I mean, the air's around us, right? Okay. It leaves behind a hole in the air. Ah, but wait a minute, the scholar said, you can't have a hole in the air because nature abhors a vacuum. So that vacuum is going to be filled up by the air. So the air is going to squeeze down and back and squeeze it right along. And so there's the force. The air squeezes it along. Saturday night when you're taking your bath, try ivory soap, the kind that floats. And you're sitting in the bathtub, and there's the soap right there. And you go to grab it. You've done that before. And you go to, oh, what happened? I keep going away from you, right? You squeeze it right through the water. Well, it was thought that cannonballs were squeezed similarly through the air, and arrows too. What do you guys think about that? Not too many people were satisfied with that, but that's the best they could do at the time. There's got to be some explanation. What's a better one? And along came an Italian type by the name of Galileo, who turned it all upside down. Everyone's looking for the force responsible for the motion. Galileo said, hey gang, guess what? No force. If I took this thing out in outer space where gravity was very, very small, I took this thing in outer space and I threw it, it might take a force to get it going, but when I let go, it'll go of itself. No force required. And so this idea that once things are moving, they'll keep moving is invoked in what's called Newton's first law. Isaac Newton came along right after Galileo. And Newton's first law says, hey gang, if there's no force acting on something, it will stay as it is. We call that the law of inertia. If something's at rest, don't mess with it, it'll stay at rest. If something's moving, Don't mess with it. It'll keep right on moving. And what kind of path? A straight line path. To say it will move in a straight line path at steady speed is to say it will move with constant, begin with a V. Check your neighbor. Try it, gang. What is it? All together. A booming resounding of all the scholars of Hawaii. All together. What's the word? Begins with a V. Velocity. All right. I thought you were going to be wimps there for a while. Velocity. See, constant velocity says constant speed and constant direction too. Ain't that true? Right? So something will move at constant velocity in the absence of a force. That's if it's moving anyway. But if it happened to be at rest, no force, what's it going to do? Stay at rest. So we call that idea, the law of inertia, Newton's first law of motion. Things tend to stay put. Make sense? I got a couple of blobs. These are blobs of clay. These clays have inertia. Right now they're at rest. They tend to stay at rest. I put this clay on the top of my head like this, and I can see this one very clearly. But you know what, gang? I can't see this one back here. How can I see that one without touching? Simply turn around. Isn't that neat? See? Things tend to stay put. You ever do that? You got a bowl of soup, right? And you got the alphabet, and you want this alphabet over here near you, so you turn the soup bowl, and what happens? The alphabet stays there. You keep turning the soup bowl. Inertia. Things at rest tend to stay at rest. Ain't that neat? Okay? Here's a block of wood. Here's a block of wood. This block of wood tends to stay at rest because it has inertia. By the way, inertia is another word for mass. Mass, another word for matter. This block of wood has mass. Gravity's pulling on it, so it also has weight. But to say it has mass is to say it has inertia. To say it has inertia is to say it tends to stay right there. That's a tendency. Now what I'm going to do is I'm going to flip this tablecloth, and I'm going to pull it like this. And you're going to guess what is going to happen to the block. Will the block stay essentially where it is? Will it recoil, come down here and hit the cylinder? Or will it follow along in the direction it's pulled? Check your neighbor. Take a guesstimate. Make a hypothesis. All right, here we go, gang. Which way? A 1, 2, 3. Staples, the staples. Hey, this illustrates Newton's 0th law of motion. That's stay on your toes, gang. Be skeptical. These little staples provided a force that made it move, see? So there was a force. But what if the staples weren't there? And what do we have down here, gang? We have some plates. No staples, no Velcro. The tablecloth. This is what I want you to do over the weekend when you get invited to dinner at someone else's house, okay? What you do is they say, hey, what are you learning at the university? Say, I'll tell you what I'd be learning at the university, okay? And get the table all set. Grab the tablecloth like this and say, do you believe in the first law of inertia? And they say, yes, we do. Hey, how about that? Not even a quiver of motion. Did you see that? Okay. See, something at rest tends to stay at rest. There's a little bit of friction force there. Now, a little bit of force does move it a little bit. You saw the motion a little bit, yeah? But if you had something really, really heavy, oh, look at this here. Look at this. Boom. Look at that thing. Hey. This has a lot of inertia. A lot. Some people get mixed up. They say, no, Hewitt. It's not got a lot of inertia. It got a lot of weight. That thing is heavy. Is it heavy? It's very heavy, okay? You can kind of just feel it, can't you? Okay? And I take this thing and I get it moving. What's pushing it now, gang? What's pushing it? Nothing's pushing it. Nothing. And that idea that it'll keep moving with steady speed with no push, it moves of its own inertia. Dig this, gang. Inertia doesn't tell you why. Oh, God. Okay. Sorry. Okay. Thanks for telling me at the last minute, gang. Sometimes you find out who your friends are, huh? How would you guys like it if I was standing like this? Oh, boy, okay. This room would be filled with people next time, right? People like violence, right? Right? Okay. Yeah. This must have touched the wall, and the wall touched it, pushed it back, huh? Yeah. So what's the force keeping it going? No force. We don't know why it keeps going. But we call that ignorance inertia. Get the idea? Nobody knows why it keeps going. We just know that it does. And so we call that inertia. Any forces acting on this ball, by the way? On this cylinder? Any forces acting on it? Right now? Yeah. Force of gravity. And force of gravity is pulling it straight down. Isn't that true? Okay. If the force of gravity is pulling it straight down, why doesn't it go straight down? By the way, is that accelerating right now? No, it's not. And if it's not accelerating, what does Newton say about the forces that act on it?
They're in equilibrium.
Zero. Zero net force. In fact, that's the idea of the law of inertia. If you see anything that's not accelerating, then all the forces that might act on it all balance out. Let me show you how this thing looks. Here's a cylinder like that. Now, there's no force this way, no force this way, but there is a force down, and that's the force of gravity. And that force of gravity acting straight down, right toward the center of the world, okay? That's its weight. If that were the only force acting, Newton says, hey, in the presence of a force, it will change how it's moving. It'll start to move. But it doesn't. That means there must be something pushing which way, gang? Up. And what's pushing up on that? It turns the table out. It turns out the table. The table is holding it up. And guess how hard the table's holding it up with? Just as much force as this is pulling down with. And so the two forces cancel out. See, if I push on this thing over here with a force maybe of 10 newtons, and someone else pushes over here with 10 newtons, what's the net force on the object? Oh, you can't do that. Let me try this one. Let's suppose someone pushes over here with a force of 1 newton, and someone else pushes here 1 newton. Do you guys know what the net force would be? Begin with Z. End with P. Zip. Another word for zero, okay? There'd be zero net force. What's the net force up and down over here? Zip. So what's the change in motion? Zip. And what do we call the change in motion? Begin with an A. Acceleration. So what's the acceleration if there's no net force? Zero. That's right. That's Newton's first law. That if no net force acts on an object, then the object won't accelerate. And we learned last time that acceleration is a 50-cent word for what? Change. You remember that? See? If there's no change, then there's no acceleration. And Newton says there'll be no acceleration if there's no net force. That's why things that are sitting at rest, no force acting, no net force, they'll stay at rest. You get something moving, no net force acting, what's it going to keep doing? Stay moving. It's going to avoid change. And that's the idea of inertia. People that way too. Some years ago, I was working, and I used to be a silkscreen printer, sign painter. I used to work for a living before I get into this. And I used to work in a factory. We used to silkscreen print T-shirts. And we have these great big drums of paint. And we'd bring over these buckets to get our little bucket filled up. And this great big guy, this big guy over here with these big things here would dole out the paint. And he used to do it with this little spoon. And sometimes that screen would be drying up. But Harry, would you hurry up, please? Geez, my screen's going to dry up. And he's going on fast as I can. He's got this spoon, and he's trying to get the spoon, put paint from one bucket to another. And this is a true story. And I said to Harry, Harry, why don't you get one of those great big soup ladles, a great big thing, 2 or 3 scoops, honey, you got it filled up. And he looked at me, kind of funny, and he says, but I've always used a spoon. And I thought to myself, wow, there's inertia. A body at rest tends to stay at rest. Do you have friends like that? People that keep doing the same thing day after day after, they don't change. There's a resistance to change, inertia. In fact, inertia in Italian is a 50-cent word for being lazy. Yeah, I'm told that lazy in Italian is inertia or something like that. Anyway, that's the idea. If you're riding in a car, someone's going to take you for a car trip across the mainland. You're going to go from one coast to the other, and they say, hey, we can go in a little Volkswagen, or we can go in a great big Cadillac limousine. Take your pick. And you want to be comfortable. Which would you pick? How many say, well, either one. No, make any difference. It depends on the color of the car. Which do you suppose would give you a more comfortable ride? All right, let me give you a hint. Begin with C. The Cadillac. Why would the Cadillac give you a more comfortable ride? It's got more inertia, more mass. See? When that Cadillac go over the railroad track, let's suppose you're going over the railroad tracks in your little Volkswagen, and in the back seat you got crates of eggs. Just come from the farm, okay? And now you're going to go over the railroad tracks in that little car. What happens? And the eggs all fly around. What happens when that Cadillac got a lot more mass, a lot more inertia, a lot more tendency to keep going straight. You go over those railroad tracks, you just keep going like that. Airplanes. Which is more comfortable to fly in, a little airplane or a big one? Which one has the barf bags? The little ones or the big ones? The little ones be having the barf bags. Why? What happened to the little plane? A little wind come. Right? Doesn't have much inertia. What happened to that big plane like this? Just move right on through, honey. How did they move? Very smooth. So more inertia means more tendency to keep on going in a straight line. You go to the store, you're getting some groceries at the store. You got the baggies, huh? You got the baggies all set, and you got all your bananas right here, and you're going to get the baggie. Do you have to put all the bananas down? Put one hand on top of the baggie thing, and then pull the other one? Do you have to do that? No, you don't do that. You keep the bananas in one hand, you grab the bag, and you snap it. And when you snap it, what happens? The roll of bag has so much inertia, stays right there, doesn't it? And boom, it'll snap away from you, huh? How about when you're reading your book and you're on the toilet? All right? What happens? You're on the toilet, you're reading a book like this. Do you have to stop when you're all through, put this down, hold the top of the toilet paper, and tear the bottom piece? Do you have to do that? You don't have to do that. You can keep reading the book, reach over, and snap down quick. And you rely on the inertia to hold it still. Isn't that true? I can kind of show you that here. Here's a ball. It's got a lot of weight. To say it has a lot of weight is to say it has a lot of what? Begin with M. Mass. To say it has a lot of mass, say it has a lot of, begin with I. So this thing has two things. Weight. It also has mass. You measure mass by how hard it is to change. You measure weight by how heavy it is. See, this is quite heavy here. But if I take this on the moon, it's not so heavy. You know why? How heavy had to do with gravity and the mass. On the moon, there's less gravity, so it'd be easier to lift. And if I took it to a part of the universe where all the gravities cancel out, put it on a bathroom scale, what would it have? No weight at all. But it still has stuff. It still has mass. If you were in some orbiting space vehicle where the gravity is seems non-existent, and this thing came by like this and it hit your head, boom, it's going to hurt. You know why it's going to hurt? Because a body in motion tends to... You got a bunch of groceries in your hand and a bag. And the bag is very, very heavy or very, very massive. And you take your hand and you bump into the wall. Ooh, ooh, you're crunched, you hurt. But if you're carrying a bag of paper towels, no problem. And you hit just the same speed. Why is it when you're carrying the bag of heavy stuff, your hand gets schmalched? And when you're carrying the light stuff, it's okay. Why? Any reason for that? How many say, oh, there's probably no reason. It's just, come on, you guys. Do you see it? Huh? Well, let's see what happens here. Here's a ball hanging by a string. Here's another string here. What I'm going to do is I'm going to pull the ball harder, 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 and snap. one of those strings is going to break. You got to be guessing which string will break. We get the scene like this. Okay. I pull down, pull down, pull down. Which string breaks, this one or this one? Check your neighbor. Take a guess. How many be saying, it's the top string gonna break because he's got the other one over here for the next trial? Let's try it, gang. Here we go. It was the top string. HC. How come? Let's look at it. When I pull this down, don't I set up a tension in this string here? And doesn't that tension also transmit it up to here? So don't I have that tension in both strings? Huh? Isn't that true? So it could be either one. Maybe sometimes it'd be the bottom, maybe sometimes the top. Except for what with the ball? Its weight or its inertia? Begin with a W. End with 8. Try it. Weight. The weight of the ball acts on which string? This one or this one? This one. Ah. So on the top, you have the weight of the ball plus the tension of pulling, and over here only the tension. So sure enough, the top one breaks. Okay? Shall we try it again? I'm going to whip the string down very, very quickly. I'm going to ask that ball to accelerate more than 10 meters per second. Because I'm going to, boom, get down like that. Not slowly like before. And watch what happens. Sure enough, the bottom string breaks. Ain't that nice? See that, huh? We can kind of do the very, very same thing here. It turns out, if it's done quickly, the top one is protected, isn't it? We can do the same kind of thing with this anvil, okay? This anvil, if I asked you to put your head underneath here, okay, and I hit it with a sledgehammer like this, and if I hit this, quickly, you'd be okay, right? Because the top string would break, but the bottom string wouldn't break, would it? So you'd be, can I have a volunteer, please? Okay, I tell you what, I'll try it. I won't put it on my head. But everything we just did with that hanging ball, we're going to do with the anvil. Same physics, okay? Can I have a volunteer to man the hammer? Volunteer, please. Okay. This has got a lot of mass, gang. To say it's got a lot of mass is to say it's got a lot of tendency to stay right where it is. Okay, I'm going to lay on here. And would you put the anvil right on my stomach, please? Right on my chest. Okay. Okay, right here. Okay. Now would you get on the other side and slam that thing as hard as you can? Over here, Troy. Oh. Please don't miss the anvil. All right. Do you have any grudges against your teachers? Hit it harder. Okay. Take it off. All right. How come I'm okay? Would you guys do that?
Are you really okay?
Yeah, I'm okay. Hey, he could hit it as hard as he wants. Make no difference. I'll tell you, there's a lot of things going on here. First of all, is it important that this thing be heavy? To say it's heavy is to say that it's also massive. To say it's massive is to say that it has a tendency to stay right where it is. And when you hit it, boom, what's the tendency of this? To stay right where it is. Let's suppose instead of using this, we used a quarter. And I put a quarter on it. How much tendency does a quarter have to stay where it is? See? So some say, gee, I don't want a heavy thing. I'll try it with a nickel or a penny, okay? Boom, you wiped out. Okay? You see what I mean? See? So it's the mass. The mass of that thing protects you. It's all right, okay? Nothing to You guys got a hammer, huh? This is a small hammer. Remember when you were a little kid and you were trying to tighten this because it's a little loose and you're going like this? Remember that? And old Uncle Harry come by and Uncle Harry says, "No, no, child, you don't do it like that. What you do is you hold it like this." And you looked at Uncle Harry and you said, "HC." And what did Uncle Harry say? You guys have an Uncle Harry? Didn't Uncle Harry say, "This hammerhead has a lot of inertia"? To say it has a lot of inertia, when it's moving, it tends to keep moving, okay? And so when this part stops, what's this part tend to keep doing? Moving. And move right down. And every time you hit it, tightens right up. Hey, huh? There's inertia. Another thing, too. Guess which acts the same way? The little hammerheads in your back. How tall are you guys? You got your driver's license. Your driver's license tells how tall you be, right? Is that the morning figure or the night figure? Do you guys know that at nighttime you are shorter than you are in the morning time? Did you know that? It's true. Scout's honor. It's true. And I'll have you check it over the weekend. You have in your back, you have a little sacroiliac, you have all these little bones like this. And as you keep going like this, walking along, boom, 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 through the day, by the end of the day, you're a little bit shorter. Do you ever see those jogger types? They start out, "Well, let's go for a run, gang," and they run, boom, boom, boom. The end of the day, "Well, boy, that was a good workout." They get shorter. Hey, it's true. You settle right down. And then at nighttime, you get in your bed, you come right back out again, you're all right, huh? Now, I got something for you guys to check. I want you to check this out. Tonight, before you hit the sack, I want you to find some part of your house that's just about out of your reach. Find some place where you can reach up and find a place. Like I used to have a room that had beam ceilings, okay? And at nighttime, I could reach up and I couldn't touch those beams. I'd reach, I couldn't touch them. Go to bed. Get up in the morning, hit them, touch them easily. Try it yourself. You really are shorter at the end of the day. Ain't that neat? What's that? Begin with a PH. Sound like F.
Physics.
Physics, honey, physics, yeah. Your height depends, it has to do with inertia. One of the rules of the game of love of the physical world is this law of inertia. The idea that if something isn't changing, then the forces all balance out. So if something stays in equilibrium, as we say, then whatever forces act, they must all balance out to zero. Okay? We saw that with the weight over here, the cylinder. The cylinder is pushing down on the table, gravity's pulling it down, but the table's holding it up, so all the forces balance out. In fact, you can say if there's no acceleration, the net force is zero. Do you understand that rule? I can remember when I didn't understand that rule. Let me tell you a true story, a thing that changed my life. When I was 25 years old, I was a sign painter in Boston. Anyone here ever paint signs in Boston in January on the shady side of the street? Honey, your paint gets really gummy. And you're trying to paint those billboards. The paint is terrible, and you're freezing, and it's cold. So you know what I did? I went to Miami, Florida. And down in Florida, I joined a sign painting crew. We used to paint billboards. You know, driving down, you see the billboards, pineapple and all that stuff, okay? I used to do that, and that's what I did for a living. I was a professional. And I was the new man in the company, and I was assigned to paint with a painter whom no one else wanted to paint with. And the reason they didn't want to paint with this guy is because there was a rumor going around about him, and it turned out the rumor was true. He was accused of all the guys in the yard of being an intellectual. And he was. Yeah, he was an intellectual. You want to paint with an intellectual? You want to paint with the boys, honey. You don't want to paint with an intellectual. You paint with the boys, you talk about what? You talk about your sex fantasies, you talk about cars, you know, or you talk about sports. Mostly sports, right? What else is in the world, huh? That's what you talk about. This guy was Burl Gray. We talked a little bit about those things. But my friend Burl Gray turned out to be my friend. My friend Burl Gray talked about ideas. ideas. 8 hours a day massaging my brain. I loved it. He changed my life. Scout's honor. He changed my life. And let me tell you, one of the little things we talked about one day took a whole afternoon. And we talked about it, and the afternoon fled right by. And it was this. We're up there painting, and I have a scaffold like this, you know? And the scaffold hangs, and here's the billboard back here, okay? And Burl will be back here, painting here, and I'd be over here, painting here. And Burl was heavier than me. He weighed more. I was lighter. And Burl one day said, you know what? These ropes are holding us up. If you take the rope and twang it, there's a tension in the rope. It's tight. And he asked, hey, would there be more tension on my side than your side because I'm a heavier guy than you are? And let me ask you that question. If you were out there in the scaffold and you got a heavy-set guy here and this is you over here, would there be more tension in his cable than yours? Which is to say, if you put like a little scale here that could read how much is being stretched, a spring scale, huh? And you put one over here too. Okay? And he asked that question. Now, we had no way of proving that right then, so it was all mental massaging, huh? Well, how about it, gang? Check your neighbor. How many people say, yeah, there'd be more tension here than here? Yes or no? How many say, oh, it'd be about the same? Everything's the same. Everything in the world's the same, man. There's no distinctions to be made. How many say, no, I think over here, this guy's heavier. I think he'd pull down harder than this guy over here. Show of hands. Well, that's what we said, too. That's what we said. Because we reasoned if these things were about to break, Burl's side would break first. Okay? Yeah. Here's another thing that was kind of neat. So I started walking over toward Burl because I wanted to fill up my paint can, okay? I'm walking over toward Burl, and Burl says, hey, Hewitt, as you walk over toward me, will the tension in my cable get more, or will it stay the same? What do you guys think? Check it with your neighbors. How many people say, oh, it'll stay the same, everything stays the same, I'm the same, you're the same, we're all the same, everything's the same? Show of hands. How many people say, no, as you get closer and closer, this tension going to increase. Because if this rope was about to break and you got closer and closer, pretty soon the combined weight would break the rope. There'd be more tension. The closer you get, the more the tension. Well, that's what we figured out, too. We figured that it would get more. If we both got here, it would really get a lot higher, right? We kind of figured that out. But you know what? Burl was an intellectual. But Burl didn't know his physics. He had never taken a physics course. He didn't know the very rules by which the physical world was governed. He didn't know physics. Very, very bright, but ignorant. Okay? So we kind of talked about that. But here's the question that really got us. And Burl was good at asking questions. Burl says, hey, Hewitt, if you walk over here and the tension here gets bigger, like maybe 50 pounds, will the tension in your side get less or stay the same as it was before? What do you guys say? How many say, I ain't saying anything? I ain't saying anything, Hewitt, because I'm good at just remembering what's said. You do the thinking, Hewitt. I'll do the remembering. I'm good at remembering. Show of hands. All right, check your neighbor. Do you think that the tension over here will get less as it gets more over here? Take a reasoned guess. Let me go over that again, gang. Let me go over that again. I'm not going to introduce the 50 this time. I think that's confusing people. Let me just say this. Burl asks this question. Hewitt, as you walk over, we agree that the tension on this side will get more. Does that mean the tension on this side will get less? Check your neighbor. E. Well, you know what we reasoned, gang? We reasoned that it would get less. And you know what our reasoning was? If we both got over on this side here and leaned out, this side here might even go up like a seesaw. See, it's kind of balancing here? And we reasoned that this side here might even lift up and there'd be no tension at all. So we reasoned that, yeah, as this side gets more, this side gets less. And here's the question that blew us out of the water that we never came up with an answer to, at least not that day. And that was, Burl said, if this side here gets more by, say, 50, will this side get less by 50? Heavy, heavy, heavy. Yes, no, maybe. Or there's no way to tell. Take a guess, gang. Oh, how about this? If this gets heavier by 50.1, will this lose exactly 50.1? How many people in here say, yeah, I'm thinking that's the case? Show of hands. 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 50. Well, you guys are doing better than we could do, because we didn't know. And you know why we didn't know? Because we didn't have any framework to hang our thoughts on. And you know what the framework to hang your thoughts on is? Here's the framework. The framework is, if you have any system that's not changing, that's not accelerating, all the forces that act on that system, this is physics, gang, all the forces that act on that system will balance out to be 0. Okay? That weight over there is not accelerating. What do all the forces balance out to be? 0. That means you know the weight acting down is just as hard as the table pushing back up. The table's holding up just as hard as gravity's pulling down. When you step on bathroom scales, that's what you're doing. Weight's pulling you down, scrunching the spring. And that's holding you up. And that bathroom scale is holding you up just as hard as gravity's pushing you down. So really, the bathroom scale takes a measure of how hard it's holding you up. And you call that your weight. But you're using Newton's first law, that you're at rest, there's no acceleration, so the forces cancel out to 0. And that's what happens over here. There's 3 forces acting down. There's the weight of Burl, there's the weight of me, and there's the weight of the board. And those act down. Now, we don't go down. We stay here. Why? Because something else got to be holding it up. And what's holding it up? This one's holding it up, and this one's holding it up. Now, let me ask you a question. If I add up this weight, and this weight, I'm going to get a number. How's that number going to compare to this force and this force added together? Check your neighbor. How many say same, same? That's right, it's the same, same, see? So that's why if this one gained a little bit, this one will have to lose. Because this and this both add up to these 3. Ain't that neat? Boy, I wish someone told us that. We didn't know that. I didn't learn that till I started going to school. And Burl Gray got me so interested in physics. Really, I didn't even know it was physics. He never used the word physics. But just the world. The world is a very interesting place. And it's even more interesting if you know what to look for. And we didn't know what to look for here. It was kind of interesting, but we were unsatisfied that we could never figure it out. And you guys can figure it out, because you know what the rule is. The ups equal the downs. That's why it stays still. What happened? You cut these ropes, what happens? Whip, boom, down it goes, okay? But because now you don't have the forces holding up. So it holds up just as much as it pulls. And you can figure these things out. You're standing on a couple of bathroom scales, huh? You got one here and one here. Let's suppose you weigh 150 pounds. I stand equally. What's each scale read? Check your neighbor. Oh, 150, that's bad. Let me say 200. Here you go. Come on, you guys. You can do 150 better too. What is it? 75 here, 75 here, right? If it's 150, yeah? Now, here's the question. Here's the question. What if you lean over on one side so you got like 100 here? Woo, what's that one read? Check your neighbor. What's the rule? Those bathroom scales got to hold you up as gravity pulling you down. So if you know one side's 100, the other side got to be the rest. Ain't that neat? All right. Here's a little girl hanging by a system. She's hanging by a rope draped over a pulley. And over here we have a little meat market scale. Okay? And that scale will be reading some value. She weighs 100. What be the reading over here? 50. One day we're up painting with our friend Harry. And our friend Harry was like very, very inertia oriented, all this time doing the same thing. And we're always telling Harry, Harry, you know what? Your life is one of inertia. You never make a change. You're always doing the same thing. Why don't you have a little variety in your life? Well, unfortunately, Harry took our advice. It turns out that Harry was painting in a bosun's chair like this. And you know how those bosun's chairs are? You're supported by both strands of the rope, and you're right there. And you want to go up a little bit, you unhook it, and you hook it right on, you kind of swing right there. You want to go back down a little bit, you missed a little bit of paint, and you tie it right on there, and you kind of swing by the two strands, and you're painting away, right? Well, it turned out that Harry had a weight of 200. And later on, we found out that the breaking point of the rope was 150 pounds. It turned out the rope had a dry rot inside. It looked like a pretty good rope, but it would break with 150 pounds of tension. You hear me? Okay. Is the rope going to break? Is Harry okay? Let me ask you a question. Or let me ask you to ask your neighbor a question. What's the tension in a rope? How many be saying the tension in that rope is 100 pounds? This side's pulling up 100. This side's pulling up 100. He's being pulled up by both sides. And 100 and 100 is 2. And 2 down, it's a wash. Honey, he's okay. Okay, do you see that? All right. One day, Harry's painting away here, and he comes up to a flagpole. He says, maybe I should pay attention to Paul and Burl. They're always telling me I'm doing the same thing. What am I going to do? I'm going to tie my rope right back in the same old place. Why don't I get off the beaten path and tie one end of the rope right to the flagpole here? That's Harry's last day on the job. HC. Check your neighbor. What's the tension in the rope if you do that? How many see he's in trouble? He shouldn't have taken our advice. Stick with the tried and the true. Don't venture off. Okay. That's it, gang. Think about that.